In the final video for this week, as a supplemental exercise, I will prove a classical statement that if you have two assumptions, connected and open, for a subset of Rn, then you are actually path connected. Now, you have to be very careful with this statement because you should remember that there is this example, a topologist sine curve. And this is connected, but not path connected. So connected does not imply path connectivity, but it's also not open. So it doesn't contradict this statement. So what this means is that while connectivity doesn't imply path connectivity, when you add an assumption, such as open, then you get that. So this is a common case that some fact might fail for silly reasons, but if you add a natural assumption, then you can actually salvage the statement. So a warning is this: be mindful that this openness will be crucial in the proof. It has to show up somewhere. So theorem, omega open, connected, it's then path connected. And this is also a good example of how do you use connectivity in practice. So the picture to have in your mind is that we have our set omega, and we want it's open. So that means that, okay, in a small ball around it, we can connect by a line segment because balls are convex. So small, you can always go a little bit further. And now if you can go up to a certain point, then you can fit a small ball around it and you can go kind of further away from it. So you get those points that can be connected to the point. And the question is really, is that set everything? And one crucial point here is that, does it have boundary? Well, if it had a boundary point, then you could fit a small ball here that you could connect everything by a curve. And then that itself would enlarge the set. And then it would be an interior point of that enlarged set, so it would not be a boundary point. So this idea implies that this set actually cannot have boundary points. But if you combine this with the idea of being connected, that means that the set, because it is non-empty, the only option is that it's everything. So there's a standard way of writing this idea of kind of always going a little bit further. And this is what it looks like. So you start from setting up. So you assume that you have an open and connected set. If omega is empty, there's nothing to prove. So you have to preclude some trivial cases. Empty sets are connected and path connected vacuously. So to do the proof now, it is non-empty, so we can fix some point x0 in omega. It doesn't matter what point you fix. And we look at the set A that consists of all the x's such that there's a path in omega that connects x to x naught. And it's sufficient to prove that A is equal to omega. Why is that? Well, if everything can be connected to x naught, so if you can connect x to x naught and y to x naught, then by concatenating the curves, you can connect x to y. So there's a standard construction. If you have a map, say from 0, 1 to x, that goes from x to x naught, and another map that goes from the same parameter interval to x, that goes from x prime to y, then you can define gamma double prime to be a map from 0, 2 to x that goes from x to y by concatenation, and it's defined by gamma double prime of t is equal to gamma of t if t is in 0, 1. So it first traverses the first curve, and then it traverses the other curve, but it has to shift the parameters by 1 to make sense. So there's a small technicality in defining concatenations, but geometrically, it's a very intuitive thing. You take the curve and you place the other curve after that. So how do you do that? You have to shift the parameterizations so that the endpoints match. Okay, so it's enough to show that everything can be connected to x naught, because then they can be connected via x naught to each other. And will you see this argument again? So that's why it's worthwhile to discuss now. So first of all, A is not empty. Why? Well, x naught can be connected to x naught. Well, what is the curve? 0, 1 to x, which is a constant function. Gamma of t is equal to x naught. Constant curve. So this is certainly a continuous function because it's constant, and it connects x naught to itself because it doesn't move anywhere. So, okay. So it contains a point. Now it's open. So suppose x is in A, then there exists a curve gamma that goes from x naught to x. I'll abbreviate this like that. Path. Now we have to use openness, and this is the part where we use openness. Since omega is open, there exists a delta positive such that bx delta is contained in omega. Now C is equal to bx delta is convex. So if we take the curve gamma prime that goes from 0, 1, so that's a little structure here. So that is convex. We want to show that C is actually contained in A. But to do that, we have to say that there's a curve that connects to any point. So to see this, we fix a point, y in C. So now, since C is a ball, we can take the curve gamma prime, that is from 0, 1, takes values in C, gamma prime of t is equal to tx plus 1 minus ty. And we saw that this is a straight line path here. So we have our curve that goes from x naught to x. We have our nearby point y that is contained in omega, and we connect with this straight line segment. Now, gamma prime is in omega, since C is a subset of omega, and the concatenation, just defined just like before, of gamma and gamma prime connects x naught to y. So we found a curve, namely the concatenation that connects x naught to y, so y is in A. But this means that bx delta is in A, so A is open. Because we found, for every point, we found a little ball that's contained in A. I mean, thinking of this is somewhat a little silly, because eventually we'll show that A is everything. So of course, everything is open, so A will have to be open, but we don't know if A is everything yet. So we have to show this kind of blindly, just by using the assumptions that we have so far. Well, the next step is showing that A is closed. Well, this one, we want to show that the boundary of A is contained in A. So take y in the boundary of A. This means that now y is also a boundary of A inside omega, we should say. A is closed as a subset of omega. And to show this, we have to look at the boundary in omega and we want to show that that boundary is contained in omega. So suppose y belongs to boundary of A intersected omega, then y belongs also to omega. So there exists some delta positive such that by delta is contained in omega. But because y is in the boundary of A, by delta also intersects A. So let's look at this picture now this way. So we have our x naught, we have our x, we have our hypothetical y in the boundary. There's a small ball that fits inside omega, and there's a point of A that's inside that small ball. So there exists an x inside by delta intersect A. But by definition, then, there is a curve that goes from x naught to x. And again, we can compose with the straight line segment. So let gamma be the curve from x naught to x from the definition. And let gamma prime be the straight line segment, again given by this usual convex combination map. It maps into C, so it maps into omega, but gamma prime of t is equal to t times x plus 1 minus t times y. So this connects x and y, and their concatenation is a curve from x naught to y, and it's continuous. So y has to actually be in A because it's by definition it's connected by a curve. A is all those points that are connected by a curve. So what we get is that every point of the boundary belongs into A, so boundary of A is in A, boundary of A intersected omega. So A is closed in omega. Technically, the openness is also in omega, but as you saw in the exam, an open subset of a open subset in the relative topology is itself open. Now, A has to be everything because omega is connected. The only non-empty open and closed subsets of A, omega, are the full space. The only subset which is non-empty, open and closed in omega has to be everything by a lemma that we showed in the Wednesday lecture. So that concludes this example. So the structure of these proofs is define the set of interest, and that should be connected to the property that you're working with. And then you show three things. A is not empty. A is open in your subset. A is closed in your subset. And finally, from these, you conclude using connectivity that A is everything. So there are three steps. Set up these checks, and then a conclusion that uses connectivity. And another thing that I want to highlight from this proof is that the point where we used openness and where the general proof fails is the second part. We needed this ball here to get the connectivity. We also needed it in the closedness. So we used this ball there. We used it twice, in fact. In this. These parts could fail, therefore, in a general case, and that's why this property does not hold in general. These slides, these notes will be available on CampusWire, so you can also see them there. Thank you. Have a nice weekend.